Hello, welcome back. In this lesson, we're going to see how to use the fast Fourier transform algorithm to compute the DFT and the IDFT of a signal. So, like we saw in the theoretical part, the FFT or the fast Fourier transform algorithm is one of the algorithms out there, and in fact, the most successful one, which is capable of speeding up the DFT computation. In fact, orders of magnitude faster than the regular DFT algorithm. It will be much faster than the algorithm we wrote in the DFT section. And this time we're going to use the FFT function which exists in the NumPy as well as SciPy to compute the FFT. And later on we shall see how to generate or develop our own FFT algorithm. So let's get to it. I'm just going to do a save as over here, and I'm just going to come out here and create a new folder known as FFT. And within this FFT, I'm just going to copy the my signals. This is where we keep all of our signals, right? So I'll copy this, come back to my DSP course folder, and then in the FFT folder I just created, I'll paste this here, and then I'll rename, and then now I can give my script a name. I'll call it FFT, and then I'll hit enter. Actually, in this example, we're going to do both FFT and IFFT. And IFFT is the same as IDFT. IFFT implies inverse fast Fourier transform. So I'm just going to clean everything here just to stop confusions so that we can start from the beginning. So over here we need pyplot from matplotlib to plot. We need numpy, we need scipy, and then we need our signal. So I'm going to start by importing our my signals module. So I'll say import my signals as 6, and then we can do matplotlib from matplotlib import pyplot as plt. Then we can do from scipy dot FFT pack. There's a module in scipy known as FFT pack which contains the FFT functions. We say import FFT, IFFT, and when we do this, rather than saying FFT pack dot FFT or FFT pack dot IFFT, we can simply say FFT. Without using scipy dot FFT pack, we always have to say FFT pack dot FFT, just like we used to say signal dot convolve or signal dot correlate, because correlation and convolution exist in the signals module. But now we've imported the functions directly from the module, so we can call the functions directly, right? So once we've done this, let's import numpy as np. I'll come here and say import numpy here as np. So let's start with the FFT. Let's create a variable. I'm just going to call this freq domain signal, right? Freq for frequency, freq domain signal. And we compute the FFT of a signal just by saying FFT, and then we pass the signal, the input signal as argument. We can say 6 dot ECG signal. We're going to use our ECG for this example as well. Once that is done, let's compute the IDFT, the IFFT, right? And this is going to be where the result of the IDFT will be stored. Time domain signal, and then this equals IFFT. And IFFT, what we want to do is we want to take the result given to us from the FFT and pass it as argument to the IFFT function. So we pass it here like this, and then we'll have this. And let's see how to find the magnitude. We can say magnitude equals, and we use the numpy to do this, np for numpy abs for absolute value, and then we can just say frequency domain signal. When we find the absolute value of the frequency domain signal, it will give us the magnitude of the signal. Freq underscore domain underscore signal like this. And this is all there is. Now all we have to do is use pyplot to plot the signal. We can start by saying style.use dark background, DARCK, background like this, and then we can create our subplot arrays. I'll say f plt underscore arr, and this equals plt dot subplots, and we need 4 subplots here, and they all share the x-axis. So I'm going to say share x equals true over here like this, and then I'll set a super title f.subtitle, and then I'll just give this the name fast Fourier transform, fast Fourier transform to brackets FFT like this. Start with index number 0. I'll say plt underscore arr underscore index 0 dot plot, and what we want to do is plot our input signal. Our input signal is sig dot ecg underscore signal, and we can give this the color of red like we saw earlier. We'll put a comma color, and then we'll pass red over here, and then we can set a title to it. We say plt underscore arr index 0 dot set underscore title, and then we can pass the title. So in Python nowadays you can use both singular quotation marks and double quotation marks, yeah, so don't worry about that. Let me just use double for my strings in order not to, in order to keep consistency really, and to separate those from these ones here. Right, so we can set a title, and the title here is the time domain signal. I'm just going to say time domain, and into bracket input signal like this, and we can set this color, give the same color as the plot, color equals red, and we can come to the second index, index number 1. So plt array index number 1 dot plot, and this time we want to plot the frequency domain signal, and we can say frequency. We can just copy the name frequency domain signal, and we can give it a color of cyan, color equals cyan, cyan, and we can do the title as well. I'll just copy this, paste it down here, change this title to frequency domain signal, change this to frequency domain, into bracket FFT, and the color here is cyan, and then we can do the other one, which is the magnitude, and after that we do the IDFT. So I just copy this, both of these, set this to 2, set this to 2, and then we change this word here to magnitude. We change this color to cyan, and the title here to change this title here, we set it to magnitude like this, and then we can do the last index, which is 3. Set this to 3, set this to 3, and then over here we want to plot the time domain signal. So set over here time domain signal, we can change the color to green, and we can say over here time domain, and change into brackets IFFT like this. So this is all we have. Once that is done, we can plot by saying plt.show. Come down here and say plt.show like this. Right, so this is it. Let's run it and see what we have. So we need to import style from matplotlib. We've not imported that, but we're using it here. If we don't do that, we get an error. So I'm going to say from matplotlib import style like this, and then Control S to save. Click over here, run module, and this is what we have. Right. So this is it. This is using the FFT function in SciPy. So over here, to identify the frequencies that exist over here, we don't need this entire signal. If we take this as the center of the signal, this side here is a mirror of this side. The right side is just a duplicate of what's in the left side. You remember that when we were designing our own DFT algorithm, we made the frequency domain signal real part and imaginary part half the length of the time domain signal. However, over here, that's not the case. The FFT algorithm in SciPy is designed to give the full length. So the right side is simply a duplicate of the left side. So we just need half of this here. If we wanted to identify the various frequencies, we just draw a straight line in the center and then forget of everything in the left side and just try to identify using the right side. So this is all there is for this. And yeah, this is FFT. It's orders of magnitude faster than DFT. Now we have a very short signal, so we don't see the difference. But if we had signals with about 100,000 points or even 1,000 points, we begin to see the importance of having a fast Fourier transform algorithm. If you have any questions, send me a message or leave in the questions area, and I shall see you in the next lesson.